Okay, this exercise 5A for Year 12 Further Maths, and it's factorising quadratic and cubic expressions which have complex roots. So it's where we're expecting to get some complex roots as part of our answers. So a little starter for you, you just got to do a bit of basic adding and subtracting and timesing. So see if you can do those. I'm going to pause the video. I want you to do the same. Do all four. This one, of course, is the division. And you're trying to do this without a calculator. You're trying to show this using detailed reasoning. This is what they'd say in the exam to prompt you to think, oh, I better show my working out. So imagine this says use detailed reasoning. And I'll probably say that a few times in this PowerPoint. I can't remember if I need to. But this one will require you to, when you do q divided by I, it's 1 plus 2i. And you're dividing by, what's I? It's minus 1 plus 3i. You should remember you have to times top and bottom by the complex conjugate. Minus 1 minus 3i. And if I was marking this, that's the first thing I'd be looking for. I'd then be able to see if you've multiplied them correctly on the top, have you multiplied them correctly on the bottom, now writing it in a nice simple way. So I'm going to stop the video and see if you can do the same. So, answers. I'm hoping you've got these answers. I'm just going to ping them up. I think, to be honest, the first one, the second one are easy. The third one, you could make a daft mistake, but it should be easy. The last one, it's easy as long as you remember what to do. So let's see if you got the right answer. See if they are what you get. And I hope they are. And if they're not, check them on the calculator and make sure I've done them right. Who knows? But if they're not the right answer, and you should have got the right answer, but you didn't, then just go back and have another look. Today then, we're doing a root of polynomials. This polynomial is a quadratic. We know that because it says z squared. The clue's in the z actually. The z will probably tell us we're not going to get exact answers. How do I write this as the product of its linear factors? Well, you probably are going to use your knowledge of the quadratic equation formula. So we can quite easily go, do you know what? We've got a equals 1, we've got b equals 4, we've got c is 13, and therefore, that's a 13, let's make it look like a 13, and therefore we can say that z equals minus b plus or minus, it's that formula that we've seen before, b squared minus 4ac all divided by 2a, and it's no different from what we've seen before. It's minus 4, notice it's all divided by plus or minus a square root of, and b squared is 16. Just do this in your head. 4 times 13 times by 1. I reckon that's minus 52. All divided by 2a, and 2a is 2. So now if I do this, I get minus 4, and the very first thing you should really do is this square root. It's minus 36. And of course that's why you get imaginary numbers. It's all divided by 2. So if I now do this square root of 36 would be 6, but it's minus 36. So I'm going to write minus 4 plus or minus 6i. That's the key. Divide by 2, so therefore I get minus 2 plus or minus 3i. Divide both of them, front and middle. There you go, there's my answers. And that's obviously z equals. It says write it as a product of its linear factors, so therefore z minus it, you can put it in a bracket, plus 3i times by z plus it. No, so I'm talking rubbish there. Z minus the other one, which is minus 2 minus 3i. Of course, one of them will become a plus. That's what it is equal to. And you can just tidy that up. You can say z plus 2 minus 3i. And z plus 2 plus 3i, if I want it as linear factors, that is. And these turned out I didn't really want it, I just wanted it as solutions. Oh, no, I did, there you go. If I write it as, there I get. Use algebraic methods to solve this equation. Now this is a cubic equation, so I'm going to have to use the factor theorem to solve this. And we can cheat a bit, we can check it on our calculator. But notice we are going to use the factor theorem. So the first thing I'm going to do is say to myself, what numbers go into this, and we're trying to, well, I'm going to write f of z equals for a start, and we're trying to find the value. If I put it into here, we get 0. That's the really what we're trying to use, that sort of little trick. And I'm going to try 3, and the only reason I'm trying 3 because I noticed 3 goes into 51, and it might be minus 3, but I bet 3 or minus 3 works. If it doesn't, it'd be 1. I honestly don't know. 3 cubed is 27, minus 5 times 3 squared is 9, plus 23 times 3 minus 51. And I'm going to just check to see if I was right. I could have used a table function on this. Plus 23 times 3 minus 51. I got 0, I guess, right. But I could have used a table function, and that would have eventually, I would have scrolled down and spotted that 3 goes in. But now I know that f of 3 goes in, I now basically divide. Now I could use the division, or I could use a method called the kx method. I'm going to use the division. So I'm going to do z minus 3. It's got to be times by something as it goes into this. And I suppose it's that something I'm trying to find. If you use the kz method, you kind of just... 23z minus 51. So let's do this division. What do you times a z by? I times by z squared. Z squared times that can be z cubed minus 3z squared. And I always say put it in the bracket to remind me to take away. So minus 5 minus plus 3, that gives me minus 2z squared. Bring down the 23z. What do I times z by to get minus 2z? Well, probably minus 2z, because I want the squared. That's right, yeah. So that's minus 2z squared plus 6z. Put it in the bracket to remind me to take away, and really it's 23 minus 6, which is 17z. Bring down the 51. I quite like the fact that it's 17, because 3 17s is 51. So what do I times the z by? I times it by 17 plus 17. And that will give me 17z minus 51. And the fact I end up with 0 here, and I take it away, is telling me it's worked. So therefore, my polynomial, my f of z, is now equal to z minus 3 from here, times by z squared minus 2z plus 17. And now effectively it says write it as its as a linear factor. So I'm going to have to use the quadratic equation formula on this. So z equals, on this one I'm going to get minus b, which is 2, plus or minus the square root of b squared minus 4 times by 1 times by 17. So all over 2 1s, which is 2 plus or minus the square root of, this is minus 68, this is minus 64, and I've got the 4 at the front of it, all over 2. And we've just seen it's 2 plus or minus 8i, all divided by 2, which of course gives me 1 plus or minus 4i. So it says, right, well, what the solutions are still equal to what I had before. It's 3, 1 plus 4i, and 1 minus 4i. That's my 3 solutions. Or if I want to write it as a product of linear factors, I'd write z minus 3, z minus this lot. So I'm going to change both the signs, and I'm just going to write it, or z minus this lot. And I think that is the right answer. Oh, did it not come up with the answer? Yes, it did in the end. I didn't need all that space, but other than that, I think it's right. Now, difference of two squares, you've seen this before. A squared minus b squared is a plus b, a minus b. But there is the addition of two squares. No one ever teaches you this at GCSE Maths, and that's because you can't really do it because you don't get any information about complex numbers. But notice what I'm saying here, a squared plus b squared is this. Now, does that make sense? Let's just multiply this out. I've got a times a is a squared, obviously. So that's that one. If I do that one, I get minus abi. This times this is plus A, B, I. Well, they certainly cancel each other out, don't they? What's this last one? It's plus B. That's plus, oh no, it's times by minus. So it's minus B squared, I squared. Ah, notice that I squared, of course, we should know is equal to minus 1. So what that has the effect of doing, well, that cancels with that. And that minus B squared becomes plus B squared. It has worked. Yes, it has worked. Now that is worth knowing. A squared plus B squared can now be factorized straight off. A bit like A squared minus B squared can be. Here's an example. Then it says 81 z to the 4. Well, straight away I'm thinking I can write this as this is 9z squared plus 4. 9z squared minus 4. It's the difference of two squares. I've spotted the difference of two squares there. What's it say? Writing your answer as the product of 4 linear factors. Now linear means I can't have squares in. So I've got to still factorize this. Well, luckily now I can. It says 9 squared plus 4. So I reckon that's 3z plus 2i. 3z minus 2i. All I've done so far is that one. Now I'm going to do this one. Well, this is 3z plus 2. No i's needed this time. 3z minus 2. And the reason why I don't need i's on those last two is because this is a minus. When it's a minus, it's a proper difference of two squares. When it's a plus, it's the addition of two squares. I think that's the answer. 3z plus 2. Oh, they've written it the other way round to me in terms of the fact that I've got proper numbers first and then, yeah, that's right. And that's the end of the lesson. Exercise 5a is what we're going to practice in class. It's a nice little exercise, but it's really going back to the basics of using the factor theorem to solve cubics, using the quadratic equation formula to solve quadratics, being able to write them as linear factors, being able to do that long division. There's a lot of work gone on there from previous maths work, and we are going to use it. And that's why people who do A-level further maths invariably do really well at A-level maths. Because you do every skill, lots and lots of times. You get better and better at them. So that'll do. Thank you very much.